Welcome to my video course on mastering ERTMS ETCS signaling systems. Before we jump into all the incredibly cool digital networks running today's high-speed trains, we really need to nail down the absolute foundational rule of railway safety, and it's this. Trains literally cannot collide if we just prevent them from occupying the exact same section or block of track at the exact same time. Sounds super simple, right? Well, enforcing that one simple rule is actually driven over a century and a half of absolutely relentless engineering innovation.
So here is our agenda for today's explainer. We're going to look at 1. Manual signaling, 2. Semaphore signaling, 3. The absolute block, 4. The automatic block, and finally, 5. Modern signaling systems.
Okay, let's dive into this historical roadmap so you can see exactly where we are headed. We're starting with steam engines and manual human intervention way back in the 1850s, then moving to mechanical and early electrical systems around the 1900s, shifting into computerized protection in the 1980s, and finally arriving at the unified digital standards we rely on today.
Section 1. Manual signaling in the 1850s.
So picture this. It's the middle of the 19th century. Railway lines are spreading everywhere, and track blocks are controlled entirely by human observation. And honestly, this created our very first major engineering problem: deadly blind spots. Railroads employed men to stand at intervals along the track with literally nothing more than hand signals and stopwatches. They would tell a driver, hey, another train passed by this many minutes ago. But you know, a stopwatch can't exactly see around a mountain curve. These watchmen had absolutely no way of knowing if that preceding train had safely cleared the line ahead or if it had broken down completely out of sight. Because of this massive flaw in situational awareness, early railway accidents were, tragically, very frequent.
Section 2. Semaphore signaling.
To give railway staff a much better way to communicate track status to moving trains, engineers introduce fixed mechanical semaphores. Just look at the juxtaposition here. On one side, you have a human watchman just kind of relying on guesswork and a pocket watch. But on the other side, you have the visual certainty of a mechanical signal. When a train was approaching and needed to stop, the physical arm of the semaphore would literally drop down into a horizontal position. It was a fixed, completely unambiguous stop command for the driver, finally removing a lot of that scary ambiguity of just waving hands.
Section 3. The absolute block. By the 1930s, the phone block system used telegraphs and telephones to actively confirm clear tracks between stations.
Section 4. The automatic block and electronic detection.
But let's face it, humans still make mistakes, right? So we needed a way to remove human communication errors entirely. Now, what's really interesting about this slide is how elegantly simple this electrical engineering solution actually is. What we're looking at is a basic DC track circuit. When the block is empty, electrical current flows from a battery, down one rail, into a relay, and right back up the other rail, keeping the signal green. But, and here's the genius part, when a train enters the block, its massive steel wheels and axles physically short the circuit. The current totally bypasses the relay, causing it to drop, which automatically snaps the signal to red. And if a wire breaks or power cuts out, the relay still drops, turning the signal red. It's a brilliant, completely fail-safe mechanism.
Another absolutely incredible method developed for the automatic block is the axle counter. Instead of a continuous circuit, this uses a super precise check-in, check-out logic. Basically, sensors count the exact number of wheel axles entering a block, and then sensors at the other end count the exact number of axles leaving. The system just compares those two numbers. If they match perfectly, boom, the block is clear. If they don't match, it means maybe a car decoupled and got left behind, so the block remains secured and marked as occupied.
Now, as we moved into the 1980s, trains got significantly faster, and a terrifying new bottleneck emerged: human reaction time. Think about it. If a driver missed a red signal at high speed, the results were just catastrophic. This totally necessitated the invention of automatic train protection, or ATP. These are systems that constantly monitor the train's speed. If a driver somehow fails to respond to a red signal or a speed restriction, the ATP system forcefully steps in, takes control, and automatically applies the brakes.
This protection actually relies on something called a safe braking model. By calculating the current speed of the train, its physical braking characteristics, and the exact mathematical distance to a potential obstacle or red signal ahead, the system generates this dynamic protection curve. As long as the train stays under this mathematical curve, we're totally safe. But the very microsecond the train's speed intersects with this curve, The ATP calculates that it's the absolute last possible moment to intervene, and it triggers the automatic brakes to ensure the train stops safely before ever hitting that target point.
Section 5. Modern signaling systems and the ERTMS standard.
So, as rail travel across Europe really expanded, standardizing train control became a critical, massive necessity. And this brilliantly illustrates the huge problem railway engineers faced at the end of the 20th century. Just look at this map. Over the years, different countries had developed their own highly effective but completely incompatible national ATP systems. We had over 20 different systems literally blocking cross-border interoperability. It was wild. A train traveling across Europe would actually have to stop at borders just to swap locomotives, or it had to be fitted with multiple, heavy, super expensive onboard computers just to read the different national signals.
The definitive answer to all this geographic fragmentation was the European Rail Traffic Management System, or ERTMS. ERTMS standardizes operations by combining two distinct subsystems. First, you have ETCS, which is the standardized onboard digital train control system, and second, you have GSMR, a dedicated wireless mobile communication network built just for railways. Together, they create one single unified language for the trains and the tracks.
Upgrading to modern ERTMS Level 2 provides some absolutely massive benefits. We get increased safety through that constant speed monitoring we just talked about. We get full interoperability across national borders, which saves insane amounts of time. We also drastically reduce maintenance costs, mostly because we're physically ripping out thousands of old line-side signals. But honestly, perhaps most crucially, by moving from physical trackside signals to virtual signals displayed right inside the driver's cab, we can safely reduce the distance between trains. This means we can run significantly more trains on the exact same infrastructure, vastly increasing capacity. It's a real game changer.
We have definitely journeyed a long way from watchmen standing around with stopwatches, all the way to continuous digital radio supervision. Now, as engineers actively develop ERTMS Level 3, which, by the way, abandons fixed track circuits altogether in favor of dynamic, moving blocks based on absolute braking distances, we really have to ask ourselves, how close are we to a fully autonomous, borderless global railway network? It is an incredibly exciting time for railway engineering. Thanks, we can see you next video.